Well, good afternoon, everybody. My name is Andrew Braham, and I'll be leading today's session of Pavinars entitled, What is Mechanistic-Empirical? The logistics of Pavinars: if you can't hear me talking right now, I encourage you to check your computer volume and or your speakers. And if those are in full working order, you can try going to the Illuminate softwares by going to the Tools, Audio Setup Wizard, and then follow the instructions for help. During this presentation, if you have any questions, I encourage you to raise your electronic hand by clicking on the hand icon below the list of participants. So if you look on the left side of your screen, you'll see a list of participants with my name, Andrew Braham, as the moderator on top. And below that list is the small electronic hand. And by simply clicking on that hand, you can raise your hand indicating that you have a question. And I will pause at a convenient break after I see the hand go up, and you can type your question into the chat box, which is directly below the electronic hand. And just so you know, professional development hours will be emailed to you after the presentation, so the email address you entered in while logging on to the Pavinar will be used to send your PDH hour. Now, if you were unable, or if you do not receive your professional development hour certificate, I do encourage you to email me directly and we will sort it out. So today we will be talking about the term mechanistic-empirical. And mechanistic-empirical is in the pavement industry these days because of what is now called the DARWIN-ME guide, Darwin Mechanistic-Empirical, which was previously referred to as the Mechanistic-Empirical Design Guide. This is a brief overview of what we'll talk about. We'll start with a background talking about the need for a mechanistic empirical design, and then go over some of the advantages and disadvantages of such a design. We'll spend some time talking about the principles of mechanistic empirical design, including application toward engineering materials or engineering mechanics, and also how it is a rational design process. And then we'll finish off with two examples using DARWIN-ME, one Portland cement concrete example, and the second a hot mix asphalt or asphalt concrete example. And we'll just go over an overview of the design process in DARWIN-ME for both those principles, and then also do just a brief example essentially showing one of the graphs shown from each one. And if you're interested in learning more about like an actual example of either PCC or HMA, please feel free to go to the Pavinar website and submit that as a possible topic for a future Pavinar. But due to the 1 hour time limit here, we really can't get into too many details. Now, there is a link at the bottom of the screen right now, and I cannot click on that and access that link, but this presentation will be posted online on the website as a PDF, so you'll be able to copy that link below. But this is a really nice link because it's actually a link to the old MEPDG design guide and a lot of the documentation that went into making the MEPDG design guide. So there's a lot of information there about kind of the background on what's going on within DARWIN-ME and the old MEPDG. And they have I think over 20 chapters going through all these details. So this presentation is pretty heavily harvested from those documents, which can be found at that link below. And in fact, actually, what I can do is during the next time someone has a question, while they're typing that question, please remind me if I don't, but I'll put that link into the chat box so you can simply cut and paste the link from the chat box. So why do we even need mechanistic empirical design? Well, in the mid-1990s, the Federal Highway Administration conducted a national pavement design review. So they contacted all of the 50 states in the United States asking, well, how do you design your pavements? And 80% of the surveyed states used either the 1972, the 1986, or the 1993 AASHTO design guides. And while these are very good tools, and they've done a lot to improve our pavement and pavement infrastructure here in the country, they are empirically based off performance equations developed from a 1950s AASHTO road test data. So states in the late 90s were using something developed off data taken 40, almost 50 years beforehand. And we'll go through some more examples of why that is kind of dangerous in our field in the next couple of slides. And what do we mean when we say empirical? Well, I looked it up in Webster's New World College Dictionary, the 4th edition, and the definition of empirical is relying or based solely on experiment and observation rather than theory. So when we talk about empirical methods within engineering, that means that, for example, we can run hundreds of tests to try and quantify how a certain material responds to that test. So we're responding based on experiment and observation, but we're not actually basing it on fundamental engineering principles such as stresses and strains and those type of concepts. And we'll go into that a little more as we go on, but in general, as we develop our design strategies, we're definitely wanting to move toward the mechanistic side of designing. So what were some of the deficiencies of the AASHTO guides, whether from 72, 86, or 93? Well, first of all, there were some climate effect issues. The test track was located in central Illinois, so there was one geographic location. Now, I did go to the University of Illinois, so I may be biased toward that part of the country. However, I do fully realize that there are many more climate types around our country than just central Illinois. Not to mention it's awfully flat, but that wasn't taken into account. In addition to the one geographic location, they only had one type of subgrade. Again, as you go around different parts of the country, there's obviously many different types of subgrades out there. For the project, they only used one HMA and one PCC mix. So all of these numbers in 72, 86, and 93 design guides were based off of only a single HMA mix and a single PCC mix placed on a single subgrade in only one geographic location. So you can kind of see how this is a pretty narrow scope. And while a lot of good data was collected, and it definitely helped advance our pavement knowledge, it really doesn't encompass what we're encountering today, where we have many, many different types of both HMA and PCC mix and mixed designs. They had only two unbound dense granular bases for base course. So again, when you think about advancements in like stabilization technologies and those type of things, this only looked at unbound granular bases. And then finally, they did not consider any sort of rehabilitation techniques. Some more deficiencies along there. The traffic loading today is approximately 10 to 20 times higher than the traffic loading in the 50s. So as you can see in the picture below, obviously, especially the semi-trucks have increased in weight and quantity quite significantly in the past 50 years. And that includes suspension, axle, and also tire pressure. For example, right now we have the new super single tires. I don't know if you've noticed while driving down the interstate, now some of the semis have single tires on each side of the axle on the back of the trailers instead of having the more typical double tires. So that's an improvement in technology in a lot of ways, but that also means you're looking at new tire pressures within those super singles, new axle configurations, and those type of things. For the construction and the drainage, they used a relatively old technique. There's been a lot of advancements in construction technologies, and also they had no subdrainage. So right now, we fully realize that having water trapped within our pavement structure is not a good thing. So we spend a lot of time designing and planning for drainage. The design life for the AASHTO road test in Illinois was only for 2 years. So right now we can design roads for 20, 30, up to 50 years if we so choose. So that's pretty limiting. And then finally, the performance is only related to the layer thickness. So they didn't look at any other material properties, any other quantifiable factors when thinking about the performance. And finally, they never validated the procedure. So they did a lot of work, a lot of good work, got a lot of information, but it was actually never validated with a second party. So as all researchers know, you try and do things perfectly, but either mistakes or oversights do occur. So by not validating this information, that really does shortchange a lot of the potential for new changes. So those are some of the disadvantages of the old design method. So what are some of the advantages of the mechanistic empirical design method? Well, at the end of the day, we want to reduce early failures in pavements, and we want to increase pavement life. So mechanical or mechanistic empirical design incorporates a significant amount of material properties into the design strategy. And by using these material properties, you can better predict how the pavement will fail. And also, a lot of design features can be directly considered in mechanistic empirical design. So, for example, you can compare the bending strain at the bottom of an HMA layer to fatigue cracking that's predicted in the laboratory. And fatigue cracking, if done correctly, is a fundamental property. The fatigue life of pavements is a fundamental property. So by using those fundamental properties, we can associate them with the strains at the bottom of pavement layers in hopes of getting a better design and a longer pavement life. Some advantages of using this design procedure from a more practical side point is that you do have, in theory, lower facility construction and rehabilitation costs. By better planning for what's going to happen in the future, you can theoretically decrease future costs. You can also reduce delay time for highway users by being more efficient with your construction. There's shorter delays. You can complete construction and then close those or open up the lanes more quickly. And finally, there's been some studies out there that say you can decrease life cycle costs by at least 5%, which means that when you look at the whole pavement life, the 10, 20, up to 50 years of pavement life, there are costs associated with the maintenance and rehabilitation of pavements. And if you do mechanistic empirical design, the theory is that you can decrease those life cycle costs up to about 5%. More advantages of the mechanistic empirical design, and this is a good time to mention that when the 1986 and 1993 AASHTO design guides were coming out, they were cognizant that there were drawbacks in the design procedures. So it wasn't like the knowledge wasn't there, but as people are well aware of, changes in specifications and design procedures do take quite a bit of time. It takes a little bit of research, understanding how we're going to best go about it. So these changes and major changes in design procedures can take quite a bit of time to implement. But some more advantages of mechanistic empirical design is that you can evaluate new loading conditions. So going back to the axle configurations, the weights that go on there, the repetitions, those type of things, you have the possibility of doing that in addition to loading conditions due to the climate. As temperature cools, especially in the northern states, the stresses build up in the pavements and thermal cracking occurs. Those loading conditions are accounted for. You can also have a better utilization of available materials. So being able to use materials in your area, run performance tests, you're able to actually understand better how the pavements are behaving in your part of the country because you're able to use those materials. There are improved procedures to evaluate premature distresses. So if there are any possibilities of premature distresses that's built into the design guide, you can look at base erosion under PCC pavements. I mentioned before that they didn't take subdrainage into account with the AASHTO road test in Illinois. But with thinking about subdrainage and thinking about the consequences of subdrainage and erosion, that can now be taken into account under PCC pavements, along with the long-term benefits of those drainage. And then I mentioned before seasonal effects are added, so kind of thinking about the climate as it changes not only from north to south, east to west in the country, but also from winter to summer, and then the fall and the spring. Those changes in temperatures are sometimes the hardest on pavements. And then finally, there is the inclusion of aging. So you can see here in the past couple of slides that there are many, many advantages to the mechanistic empirical design strategy. Now, however, unfortunately, with all these advantages, there are some disadvantages. One is cost, and the most recently available ME design software within pavements, as I mentioned, is the DARWIN-ME, and that costs approximately $5,000 for an individual workstation, which is a significant investment for small companies and for DOTs, and even for larger companies. You are able to buy a site license from $20,000 to $40,000, depending on the needs that you have. So if you're a larger company, you're able to get a slightly cheaper price, but still $20,000 to $40,000 is a significant investment for design software. There is added complexity with the evaluation of new loading conditions that ask for more traffic data. So, this is what you put in will determine what you get out. So if you want a more comprehensive result, you're going to have to put more comprehensive information into the design. So the loading conditions is one thing that is added, in addition to significant amounts of climate data. So they actually use the LTTP climate sites around the country in your iterations. However, when that happens, you can have up to 15 minutes per run. So when you're doing these iterations, we're getting spoiled by computers being able to do things so quickly. When we did pavement designs by hand, they took longer than 15 minutes, but now we would like to be able to do multiple designs, in a morning and be able to really get some ideas out and see what's best for our conditions. But as you add more inputs, it does take longer for it to run. And what I think personally is one of the largest disadvantages is the whole theory of a black box. Because you put all this information into the program, things happen, you press run, and 15 minutes later, boom, you get an answer. But there are many tasks going on in the background. And I think as engineers, one of our jobs is to determine if those tasks are doing what they should be doing. And when you put things into a black box and you get an answer out, there's really no way to verify or validate if things are performing as they should. So the software is very high quality, I have no doubt about that, but at the end of the day, it's really difficult to verify whether or not the answers you are getting are appropriate for your needs. Now the last bullet here I listed, it's kind of an advantage and a disadvantage because there are 3 levels of design inputs, and I'll give specific examples of such inputs for both hot mix asphalt and Portland cement concrete later on. But there are 3 levels, and they get, as the level increases, the amount of input you need to put into the program decreases. So for level 1, both site and material specific inputs are necessary. You need to run tests with your material. You need to input data specifically from your site. Level 2 is kind of an intermediate one where you use correlations to establish your inputs. So you may have some performance data, you may have some material characteristics, but maybe not all of them. So it allows you to use correlations. And you can run what's called the level 3, which is where you just simply use regional or national defaults. And this can give you a very broad picture of what could possibly happen, but by using defaults, you're really kind of opening yourself up to unknown possibilities to the final result. So advantages, disadvantages of mechanistic empirical design. There are a lot on both, but I think that as we move forward, this is what we'll be using. So hopefully as we move forward, we'll be able to minimize some of these disadvantages. So at this point, I welcome any questions. If you do have a question, please simply look underneath the participant box. There's a little hand with a green arrow pointing upward. You can click on that, and that will allow you to type in your question into the chat box below. All right, well, it doesn't look like there's any questions. Right now, I'm also trying to put the link. So I just put the link from, I'm going back a little bit here. Some people joined us a little late. But when we talked about the overview of what we'll talk about, I mentioned the NCHRP 1-37A report. And this is the report that developed the MEPDG software. And when this report came out, there were a lot of documents produced along with the software that described what was happening within the MEPDG software. A lot of the information I got from this presentation is from those reports online. But that link there should take you to the list of reports. And there'll be 3 columns. There'll be the manual, which has the chapters, and then the chapter titles. And then you just simply click on the green circles to the right that say Go. And that downloads the corresponding PDF. So you can really look into what you want to, but there are a significant amount of documents available to sift through there. So I'm going to scoot ahead again back to here. So we've gone over a little bit of the background, and now we're going to talk about some principles of MEPDG, or mechanistic-empirical design, excuse me. So what is the point of mechanistic-empirical design? Well, what we want to do is we want to apply engineering mechanics and rationality to our pavement design process. And what we need to do in order to achieve that is bridge the measures and the causes of distresses. So what are some measures that we have in pavements? Well, we have stresses and strains in the pavements, and then we also have deflections. So these are 3 examples of engineering measures that we can actually go out and measure either in the field or we can measure in the laboratory. And then we're trying to combine those engineering measures with the physical causes. And at the end of the day, why do pavements fail? It's because of the loads that are applied on those pavements, whether they be caused by traffic or by the environment. And all other physical causes can include the material properties of the pavement structure itself. So what type of materials are you putting in there? Are you using a hard or a soft aggregate? Are you using asphalt concrete or Portland cement concrete? All of these things can definitely lead to different engineering measures. So we're trying to link the engineering measures and the physical causes. And there's really 2 options available for mechanistic empirical design. You can either use a multi-layered elastic system or finite element modeling. And DARWIN-ME uses kind of a combination of both of those. But we'll start with talking about multi-layered elastic systems. So you can see in the picture on the bottom here, this is a cross-section of a pavement. It's actually a pavement down in Little Rock, Arkansas on I-630. At the bottom of this pavement structure is the subbase. That's the brown dirt. And then there's a thin layer, about 6 inches, of asphalt stabilized base. And then there was about approximately 15 inches of Portland cement concrete on top of that. So when you're thinking about trying to define the pavement structure in these layers, you can really see that nicely in the cross-section of this pavement structure down in Arkansas. Now when you're using multi-layered elastic systems, you do assume that material properties in each layer are homogeneous. Obviously, Portland cement concrete and asphalt concrete are heterogeneous materials, but you're assuming in the multi-layered elastic system that they are homogeneous. You're also assuming that each layer has a finite thickness, and this makes sense for the upper layers. Obviously you have 12, 15, 18 inches of Portland cement concrete, sometimes more, sometimes less. But when you start going down, especially into the subgrade, the natural base, you also assume that that has a finite thickness, when in theory, when in actuality, the subbase is essentially infinitely deep when you're thinking about the material property reactions of it. You're also assuming that each layer is isotropic. And when you say isotropic, that means that the properties are the same in every direction. So whether you're looking longitudinally or transversely or down into the pavement depth, you're assuming that each layer has the same material properties. You're also assuming full friction at the layer interfaces. So that means between, as in this picture, the Portland cement concrete layer and the asphalt stabilized base layer, you're assuming that there'll be no slipping. There'll be no surface shearing or moving between those two layers. And the same between the asphalt stabilized base and the base course below that. So this is a very difficult thing to even recognize if it's occurring in the field, if there is slipping. There's mechanisms that you can measure it with, but it's not relatively available. So this is a pretty important assumption to say that they're not moving against each other. And then finally, you have only two properties on each pavement layer. You have the Poisson's ratio and the elastic modulus, which is mu and capital E. So these are all the inputs that you put into the multi-layered elastic systems. And what can you get from these multi-layer elastic systems? Well, you have the three normal stresses, which is simply the load over the area. You have normal stresses in the Z, the R, and the T direction, or the Z, the X, and the Y direction, depending on if you're using or radial and tangential, or if you're using the standard coordinate system with X, Y, and Z. And these different forces act perpendicular to the element faces. So if you look at the little cube on the right, you can think about how that cube is a section of pavement. And there are stresses on each side of that cube because of the pavement sitting directly next to it. So you have both the stresses and then also both the normal stresses and also the shearing stresses. So the normal stresses are going in and out of the cube, and the shearing stresses are alongside the cubes. And you have 6 different shearing directions in a combination of each one of the directions. And those act parallel to the element faces. So from the previous slide, we knew that we had the elastic modulus, or big E. We knew we had the Poisson's ratio. And now we have the stresses. So with those 3 components, we can obtain the strains. And those are shown there in the general equations below. So the strain in the Z, the strain in the R, and the strain in the T direction are all functions of the elastic modulus, the normal stresses, and then Poisson's ratio. So these 3 equations are kind of the foundation of the layer elastic theory, which can be used in mechanistic empirical design. And those general equations are used for 3 properties. First, we want to find the relationships between the stresses and the strain, which are those 3 equations. And we want to determine if they're linear or nonlinear. Asphalt concrete, as it gets warmer, it becomes nonlinear. As it becomes colder, as it goes down below freezing, it becomes more linear. So these are different things that you have to take into account based on the time of day and the time of year. You're also looking for time dependency of strain under a constant stress level. And basically what this is saying is the material viscous or is it non-viscous? And on the right we have the Maxwell viscoelastic model, and you can think of that as a spring and a dashpot in series. If the material is non-viscous, that dashpot acts on a smaller level, and if it the dashpot indicates the viscosity of it, whereas the spring indicates the elasticity of it. And that goes into the 3rd bullet point, which is the degree to which a material can rebound or recover strain after stress removal. So a tire going over a pavement, it puts a stress on there. As that tire moves away, you may expect some rebound, and that would be if it's plastic or elastic. As that tire goes over the pavement, you may expect some deformation. That would be a viscous or non-viscous. And then you have to recognize whether or not these are linear or non-linear relationships. So you can see how, based on those relatively simple equations of stress and strain, now we're introducing these new concepts which make things even more complicated. And this is where something like the ME Design Guide, or the Darwin-ME Design Guide, is really powerful because it does start to take these into consideration. So along with the multi-layered elastic systems, the mechanistic-empirical guides can also use finite element procedures. And what finite element procedures are is they simply divide your pavement in your pavement layers into small and discrete portions. So if you recall that box a couple of slides ago with the shear and normal stresses on it, that's essentially what finite element simulation does. It makes a whole bunch of small little boxes. And those boxes are called elements, and at each corner of those boxes you have what are called nodes. And what you can do is you can assign a behavior to each element. And that's done through something called shape functions and equations. But you can essentially treat each one of those boxes or each one of those elements as a small chunk of pavement, so it has certain properties to it. And as a load is applied to all these small little boxes or small little elements, depending on what properties they have, they will expand or contract, they'll compress, they'll move against each other. All of these things will be happening. So that's kind of the fundamental relationship of finite element modeling, is taking these complicated structures and dividing them into very small portions. And when you do that, you can then break it down and measure how the pavement or how the simulation deflects. So once you have a behavior to all these elements, you assemble them. You can see a picture of a finite element mesh below there. So you have all these different elements in there, and between each layer you define what are called boundary conditions. So between, for example, the Portland cement concrete and the asphalt stabilized base, you need to tell the model how to relate that layer. So how does that top layer move, or how does it be restrained against that bottom layer? And once you have all of this, you can solve these functions and equations after putting loads on there, and you can get displacement values, and you can get stresses, and you can get temperatures at the nodes. So when you're talking about incorporating climate data into here, that's another example. So this gets very complicated very quickly. One of the things about finite element simulations is you can have programs, you can purchase programs to run these simulations, but they can be very dangerous as well to use, because if you don't put the proper inputs in, or if you don't assemble it correctly, you can still get numbers out, but you're not sure if it's actually giving you realistic predictions. So the multi-layered elastic systems is one way of mechanistically predicting pavement performance. Finite element simulations are a second way, but we're talking about mechanistic-empirical. So what is the empirical portion of this design? Well, the empirical portion has a lot to do with relating the materials to the inputs, for example, the traffic and environment, to the material properties, and also relating the field performance data to accumulated damage. So when you're putting inputs in, you can also put actual damage that has occurred on other, say, similar roads, but then that damage needs to predict what will happen either on new roads or future roads, and they use transfer functions in order to do that. And what they can also do is you can look at damages at critical locations. So you don't need to necessarily look at a full 10-mile project. You may know that there is one spot with a weak subgrade, or you may know that there's the one spot that's going over an overlay of highly damaged existing roadway. So you can identify areas of where you may think distresses will occur. You can focus in on those areas. But that is another step of imperialism that kind of takes away from the mechanistic design. So we've gone over the background, we've gone over some principles, but now we're going to go into some examples of Portland cement concrete and how Portland cement concrete is used for with DARWIN-ME, the Mechanistic-Empirical software that will probably be most commonly used for pavement design. Before I go on, are there any questions? All Alright, I'm not sure if I'm putting everyone to sleep or saying everything perfectly, or if everyone's lost. But if you do have any questions, please do feel free to interrupt or raise your hand, and we can address them as they come along as well. So when we're thinking about a Portland cement concrete and DARWIN-ME, the first thing I'd like to do is kind of go over the overview of the design process. And with DARWIN-ME, you have two options for Portland cement concrete. You can either use jointed plane Portland cement concrete, or you can have continuously reinforced Portland cement concrete. And when you're thinking about what sort of inputs you need to do and how to go about using the DARWIN-ME software, this is the design process that you would use in order to do that. So the first thing you'd like to do is a trial design for your specific site conditions. So you'll want to identify the traffic, the climate, and the foundation for the site that you're looking to do a pavement design on. Once you've established that, you want to define your material properties. So on the next slide, we'll talk about what some of those material properties are for Portland cement concrete. And you'll also want to do your design and construction features. And if you recall, there are three levels: the level 1, the level 2, and the level 3, which as the level increases, you decrease the amount of details you're putting in about your specific site and your specific area. Once you've inputted all those values, you need to establish your criteria for acceptable pavement performance at the end of the design period. And what does this mean? Well, for a jointed plane concrete pavement, or JPCP, you would input how much faulting, how much cracking, and what the final IRI is that is acceptable for your design period. Obviously, when you're designing pavements, you do expect some deterioration over time. So at the end of your design period, what is the acceptable amount of these distresses? And for CRCP, the continuously reinforced concrete pavement, you put in your punch-outs and your IRI. So you're kind of saying at the end of the design, this is where we expect the performance to be at. You next want to select your desired levels of reliability for the performance indicators. So when you talk about the concept of level of reliability, you're saying that there's uncertainty. You're not sure exactly how much faulting there'll be. You're not sure exactly how much cracking there'll be, but you can assign a distribution to it, saying that, well, it'll be this much faulting plus or minus 5%, or this much cracking within a 95% confidence interval. So it takes these large amounts of uncertainty and variability in both the design and the construction process and says, this is the range that we're comfortable with. And what you come up with is a variation of performance around a mean prediction. So your acceptable pavement performance is that mean prediction, and then you do anticipate some sort of variation around that mean prediction, but that's something you really can't control. And we'll see a slide example of that too a little later on. Once you've done those 4 steps, you then utilize the design guide to accomplish the following. And this is where what I referred to as the black box came in. So we've told the design guide what our traffic, climate, and foundation is, what our material properties are. We've told it what kind of acceptable performance there is and the level of reliability for that performance. We have all of that as inputs, and now the design guide takes over. And first, it computes the structural response. So you have your stresses and deflections computed, and for the jointed plane and continuously reinforced concrete, you use finite element models, and you have axle types and loads. So you can see it kind of breaking down here. We're giving it all of these inputs, and then we're getting these structural responses as outputs. And each month, the calculated accumulative damage is measured. And this is a nice feature because that way you can see how things change over seasons. Maybe during the winter there is more damage. Maybe during the spring or the fall, when you have these temperature cycles, there's more damage. But you can actually see each month how that progresses along. And you can predict the key distresses using these models month by month. And then finally, the last thing that happens is there is a predicted IRI, or predicted smoothness. I apologize. IRI stands for International Roughness Index. And you have a predicted predicted IRI based as a function of your initial IRI. So when even a brand new pavement does have a slight amount of roughness, but you predict future roughness based on that initial roughness. So then you can evaluate the expected performance at a given reliability. So you get the answer back and you find out what kind of reliability level are you looking for. Are you looking for 95% confidence? Are you looking for 50% confidence? That will dictate how wide of a range of IRI you can have, or how wide of a range of cracking or punch-outs. And if you are not happy with that performance, you can modify your design and you can repeat until your design meets criteria. So you go through the process, approximately 15 minutes later you get a number. If things aren't looking as you would like them to, then you can do an iterative process. You can change layer thicknesses, you can maybe use slightly different materials, all these different things in order to get to where you need to be. So here's an example of a required slab thickness for jointed plain concrete pavement. And on the y-axis we have the design thickness. So this is from 9 to 10 inches on the y-axis. And then we have the reliability. So how reliable do we want our study to be? Do we want a 95% reliability, which is on the far right, or do we want a 50% reliability, which is on the far left? You can see in the small box within the graph, it gives the amount of trucks, the amount of easels. It gives a climate type. It talks about joint spacing, what type of material is below the JPCP, and it also gives you some material properties. The MR is the modulus of rupture, and the EPCC is the static modulus of elasticity for the Portland cement concrete. So there's all these inputs you put in here, and then you can say, well, we're looking for a reliability level of 95%, which would give you a thickness of approximately 9.8 inches. Or if you want to go down to a reliability of only 50%, it would be a thickness of 9.2 inches. Now, sometimes the reliability range gives you a greater thickness design, depending on the materials, depending on the climate. This is a relatively narrow band, but you can see as you increase your reliability in general, you do increase your thickness. And as I've been mentioning, there are 3 levels of design input. So for level 1, this is the most detailed design input you can have. And you have site and material specific inputs for the project, and this has to be obtained by either direct testing in the laboratory and in the field, or measurements taken in the laboratory or the field. So for example, you could collect laboratory values of MR, which is modulus of rupture, or the flexural strength, F prime sub C, which is the compressive strength, F sub T, which is the split tensile strength, and E sub T, which is the static modulus of elasticity at 7, 14, 28, and 90 days. You also have the measured traffic volumes and the weight of vehicles. So you have a lot of details at the level 1. You're putting in a little more effort up front to get more details and more analysis in, which will take a little more investment up front, but in theory you're getting a better design out the back. However, they have provided 2 more levels, which, for example, level 2 is where you use correlations to establish or determine inputs. So for example, you only need the lab values of the compressive strength at 7, 14, 28, and 90 days. And the program DARWIN-ME will automatically give you correlated values for the MR, F sub T, and E sub T. So you've decreased your testing significantly, by probably over 75%, by using just the compressive strength. However, then you're moving into the thoughts of using correlations established by other groups, maybe other climates, other materials, so there's some risk associated with that as well. And finally, the last level, level 3, is using inputs from national default values. An example of this is you can estimate the 28-day compressive strength of the concrete. So you simply just enter in a default value of typical concrete. You know, we know that there's ranges out there, and you can just put a default value in. Another example is using AASHTO soil classifications to determine resilient modulus. So instead of actually going out and taking samples from the field and directly measuring the resilient modulus, you just classify the soil and then that can give you a resilient modulus. So as you increase levels, you get less detailed, but it does decrease the amount of testing you need to do and the amount of work you need to do up front. So that is an example of Portland cement concrete, and the next example we'll do is for hot mix asphalt or asphalt concrete, but I'd be happy to entertain any questions now. So as we move on for asphalt concrete, again, this will be very similar to the Portland cement concrete, but the details that go into each step are a little different. So for hot mix asphalt, the overall design process, just like Portland cement concrete, you start out with a trial design for specific site conditions. However, the conditions you're interested in for this design are much different for hot mix asphalt versus Portland cement concrete. So you can see for HMA, you're looking for subgrade support and your HMA-based material properties. So those are slightly different than the Portland cement concrete, but similar things include traffic loads, the climate, the type of pavement you're doing, your design strategy, and also construction features. So some similarities, some differences to Portland cement concrete. The next bullet, the acceptable pavement performance for the end of the design period, you're looking at much different types of pavement distresses for hot mix asphalt. And we covered this a little bit in a previous presentation, the asphalt concrete maintenance principles. But for HMA, you're looking at rutting, fatigue cracking, thermal cracking, and again, IRI. So these are the distresses that you are trying to predict in the HMA design strategy. Like Portland cement concrete, you need to select a desired level of reliability. You need to input your monthly values for traffic and also the seasonal variations for the entire design period. So you're getting into a little more work needing to be done before the design process. But like Portland cement concrete, once you input all of these things into DARWIN-ME, you come out with the structural responses, the stresses and the strain. And you can use either multi-layer elastic theory or finite element models. And you need to know each axle type and load throughout the design period. So there's a little more flexibility with HMA versus PCC in terms of the models you can use, but you're looking for the same thing. You're looking for the stresses and the strains, which is the key to mechanistic empirical design. So once you know those stresses and strains, you calculate the accumulated distress and or the damage for the entire design period, and you can predict the key distresses by performance models provided in the guide. So the guide has done a lot of calibration internally, so it knows that based on certain inputs and certain outputs from those inputs, you can predict key distresses. You can also predict the smoothness as a function of the initial smoothness, like the Portland cement concrete, and the distresses that accumulate over time. And finally, you evaluate the expected performance at a given reliability level. So it's a real broad overview. Both Portland cement concrete and hot mix asphalt, you enter in the material properties and the site properties. You enter in the traffic environment. You put those into the DARWIN-ME program, and then the distresses and damage comes out of the program. And you say, is this an acceptable amount of distresses and damage? If it is an acceptable amount, then you have your design. If it's not an acceptable amount, then you need to modify your design and repeat until it meets criteria. And we also have a probabilistic approach for HMA. So this is an example of the level of reliability. So we're talking about the rutting, which is here on the y-axis. what kind of level of reliability do we want? In this graph here, we're looking at design life of 25 years. Our critical value is 0.4 inches of rutting. And then that line is the predicted rutting from DARWIN-ME according to the inputs that we put in there. Now that line goes through 25 at one point, but you can construct a 95% reliability curve around that. So you're 95% sure that rutting will be between or underneath that curve, and that looks like a critical value. If it's a linear scale of approximately 0.2 to 0.4, you're 95% sure that it will be under 0.4. So if you're willing to accept as a designer the 95% reliability, then this seems like a good design. And this normal distribution, how does it get created? What determines the amount that it spreads? Well, it varies due to your traffic levels, your material properties, your construction quality, and those other inputs that can be put in there. Again, much like Portland cement concrete, there are 3 levels of design input, level 1, level 2, and level 3. Again, level 1, you have a lot of site and material specific inputs for the project, so you need to obtain those by direct testing or measurements. And some examples is dynamic modulus of the mixture, or E-star, or also, and that's for hot mix asphalt mixtures, the combination of aggregate and asphalt cement. And you also need to use superpave binder data, for example, G-star, which is the complex shear modulus, the sine delta, where delta is the phase angle, the S, which is the creep stiffness, and the M value, which is the rate of change of creep stiffness versus time. So we have all these different measurements that we can take of the materials in order to get the best design. If we don't have the right resources or the ability to do all of that advanced testing, we can move on to level 2, which is where you can, for example, use a sieve analysis or just simply put in the PG or viscosity grade of the binder. Obviously, the PG grade is dependent on G-star, sine delta, S, and M values. So by inputting the PG grade, that will give an idea of the possible performance, and you can correlate that to the final performance. And then finally, for level 3, you use a lot of inputs from national default values, and again, you're using kind of the less performance testing, more sieve analysis, PG viscosity or penetration grade, and also, like we used for Portland cement concrete, the AASHTO soil classification instead of using actual resilient modulus values from the soil. So in summary, for those of you who have joined me before, I switched things up a little bit, and I'm going to do the logistics and then I'm going to do the summary slide. So just so you know, the PDH hours will be emailed to you after the presentation. I actually have a meeting right after the presentation, so it may be later this afternoon. But you will get a PDH certificate emailed to the email address you put in when you were logging in. You can rewatch these Pavinars through the website. And again, please, if you have topic suggestions, please submit them via the website. Next spring's Pavinar schedule is based on topics submitted through the website and people suggesting topics. So the topics that I cover are up to you guys. They're up to the audience. So if you have things that you're interested in, please submit topics. The next Pavinar will be Tuesday, February 7th. I'm taking January off. Our winter break is from, I think, like December 22nd through January 13th. And so I'm going to skip January. I'm going to get some other stuff done the first couple weeks of January. And I figure, you know, there'll be a lot of people on vacation and stuff. So the next Pavinar will be Tuesday, February 7th. And it will be an introduction to PCC mixed design. So this is kind of taking a step back and looking at how do we take these materials, put them together, and get a PCC mixed design out the door. But other topics next spring will include hot mix asphalt mixed design, white topping, and also hot in place recycling. So a little bit about mixed designs, and then a little bit about some pavement maintenance, a little bit of pavement rehabilitation options that are becoming more popular and there's been an increase of interest in. This schedule is all posted on the website under upcoming Pavinars, so you can also get that information from there. So today we went over a nice background of mechanistic empirical design. We kind of talked about the concepts of pavement design previously and how things have changed over the years a little bit. We went over some principles of mechanistic empirical design. We saw how, kind of at the end of the day, mechanistic empirical design is talking about stresses and strains. But that's the very first step, and then you can build on complexity and look at many different factors off of those stresses and strains. We were able to go through a brief example of the inputs and then one of the outputs to PCC and also for HMA. So if you do have any questions, I encourage you to raise your hand on the left, and please type your question in the chat box. All right, well, if there are no questions, thank you very much for attending. I appreciate it. Thank you, Alex. As I mentioned, if you have topics, please submit them on the website, and I hope to see you all over. Oh, we've got the CSX22 number 2. He raised his hand, or she? I apologize. So there may be a question coming. That'd be Casey. Okay, Casey, did you have a question? I don't, you can take your time typing. I realize the typing format's not necessarily the most convenient format, but if you do have a question, please raise your hand again. Oh, okay. Oh, well, thank you, Casey. I appreciate that. Well, I hope everyone has a great holiday break, and we will see you all next February. Thank you very much. Take care.